Okay, recording on, we are back. Again, the topic is Drake's equation, trying to estimate the number of alien communicating galaxies, civilizations in the galaxy, based on breaking it down to a product of other, hopefully simpler parameters. We've covered the star formation rate, we've covered the topic of planets, how many there are and how many of them are hospitable. We've talked about development of life and on intelligence from life on those hospitable planets. And now we're left with the final two parameters, the capability of an intelligent civilization to communicate across stellar and interstellar distances, and the longevity, how long these would actually last for or survive. So here, as we already said, technology develops very, very fast once intelligence is present. And once you start mastering a technology, on the human case, it was fire, it's not very long on an evolutionary or geological or astrophysical timescale before you are able to master successively more complicated levels of technology, eventually reaching the point of being able to communicate at least into space or to explore the space near you, at least the stellar system. So again, we had about 1 million years between mastering fire and agriculture, but then only 10,000 years from agriculture to the present day, where we can send people to space, land rovers on the moon, land rovers on Mars, land a space probe on an asteroid and bring it back to the Earth for analysis. All of these developments happen very quickly. The crucial one, or the one considered crucial in studies of extraterrestrial intelligence, has typically been the radio. Because while there is an impediment and a technical difficulty in sending living creatures or even robots off to another star, that is, you need a lot of fuel to do it. And in the homework, you'll calculate just how much fuel you need to do it. It's a lot. Radio doesn't require fuel. You can broadcast electromagnetic radiation very easily. And that we've been doing for over 100 years, maybe even getting close to 150 years by this point. And of course, weak transmissions will not get very far, but it's also not very, very difficult to reach the level at which you can create transmission that would reach quite far. The atmosphere itself might hurt your transmission, similarly to the entire space between you and the nearest star. If, for example, you aim it well, or if you know where you're trying to get, or to get the signal to, etc. So we expect an intelligent species to be able to develop communication quite surely, with a very high probability. So again, this is just an estimate, but we estimate this fraction of civilizations able to communicate above 10%. So maybe 10 to 100% of them will eventually reach that ability. Might take a while. It took us 1 million years, counting from fire, 4 billion years from the stabilization of conditions on Earth for life to develop, but it happens. And as we saw, stars live for very, very long, and we've had enough time to develop this ability. So we estimate this FC as a high number, close to 1. However, we don't have any good estimates for L, the longevity of a space communicating civilization. We have a reasonable lower estimate. That is, we've been doing it for about 100 years and still haven't gone extinct. We still did not destroy our own planet in some nuclear catastrophe or global warming, financial crisis. The pandemic was a nice exercise in how the world reacts to an emergency. And we survived fairly well Even the economy didn't suffer too much on a global scale. It doesn't seem like it's such a quick process. Nuclear annihilation has been a concern for a while. It was a very big concern during the Cold War. It still is a concern with proliferation of nuclear technology. And that proliferation is, of course, intimately related to this technological advancement scale, because as we saw, radio from about 100 and something years ago comes very quickly after the Maxwell equation. And once you have radio and have Maxwell's equations, you very quickly realize about or understand or discover radioactivity. Once you have radio and can measure radio, you will notice nuclei that are unstable and atoms that are unstable emitting these radio signals or radio emission. That's historically how we discovered, of course, the structure of the atom, its energy levels, and then quantum mechanics, and internally analyzing the nucleus, discovered, of course, nuclear power, and we're able to harness and use nuclear power for both civil power production and for warfare. So we expect this, this wasn't more than 100 years between radio and nukes, and so in some sense the clock, the sand clock, counting how long a society has to survive once it discovers radio until it is nuclear capable and might destroy itself in that fashion. The clock is ticking and the sand is flowing, but we don't really know how long it would flow for. So we only have kind of a lower estimate for L, and it entirely depends on your social and humanistic optimism or pessimism, guessing how long this would actually last for. This kind of energy development or technological development has historically also been quantified in some rough fashion in what's called the Kardashian Scale, which tries to classify civilizations by how much energy they're able to harness and to use and how much power they can produce. Originally, Kardashev discussed 3 civilizations: type 1, type 2, and type 3. A type 1 Kardashian scale civilization means a civilization able to use all the energy available on its home planet. That would be 10 to the 16 watts on Earth. A type 2 civilization will be able to use all of the power coming from its own star. So its entire solar system, almost all the energy in the solar system comes from the central star. That's about a factor of 10 in power production. A type 3 civilization will be able to harness all of the energy in its own galaxy. So for example, we only expect one type 3 civilization to exist in any galaxy at any given time because it's basically occupied and used all of it. This suggests or hints at a logarithmic scale. And in fact, Carl Sagan, famous science fiction author, defined the Kardashev scale K as a continuous parameter. You'll see this is very similar to the magnitude parameter for stars. It's basically saying take how much power the society or civilization is able to produce or use, log on base 10 minus 6, so it kind of matches up with the Kardashian scale, and you get this K. So again, if you put 10 to the 16, you get log of 10 to the 16 is by base 10 is 16, minus 6 is 10. That gives you a 1 Kardashian scale civilization. If you put 36, you get that the log is 36 minus 6 is 30 divided by 10, you get type 3. So this is kind of a scale which goes up in type of the civilization logarithmically by the power consumption or power usability. And if you use this definition, then you find that our own planet Earth and our own humanity is not yet a type 1 civilization on this scale. Our production is approximately 161,000 terawatt hours over a year. If you divide that by the length of a year to find the actual power, that is energy per unit time, you get about 18.4 terawatts. Tera is 10 to the 12, so we're not yet at 10 to the 16. So our K is approaching that. We're about 0.73 on the Kardashian scale. But we're growing, which can be considered either a good thing or a bad thing, but we're using more and more energy and advancing on the Kardashian scale. It's expected that around round values of the parameter K, that is, when you approach 1, 2, or 3, when you're about to exhaust all the energy available at whatever scale you can operate, that is when humanity approaches K of 1 and exhausts the energy available on the Earth, it would drive either one of two things. One is expansion outside of the Earth or the solar system or the galaxy. You'd typically move out of wherever you are when there are no longer enough resources to expand your use of them. So this is, of course, historically why societies would roam into new territories and push out other weaker peoples when they ran out of food or foraging space, why we crossed the Atlantic Ocean and established colonies on new continents. When society grows and population grows and energy consumption per population grows, before you run out, you start kind of looking to the side and trying to expand outwards. So these 1, 2, and 3 Kardashian scale civilizations would indicate that when you approach there, you'd expect the civilization to try to move outwards and move to the next stage. And to some extent, you can say this is happening now to humanity, finally reaching the moon and now restarting the attempts to colonize or to explore for colonization, either the moon, Mars, the asteroid belt, or kind of expand out of our own Earth, because we're close to exhausting, or we fear that we might be exhausting the planet's ability to sustain our society at high energy consumption without completely destroying the planet or ourselves. So outward expansion is one of these outcomes when you come close to a round Kardashev number. The other one is failure to expand outwards, leading to a fight over resources and mass extinction. And we also saw this repeatedly in human history when there was no new continent known of to be found, or whenever peoples thought that they are running out of resources in space and would push each other and kill each other off on the fight for whatever scarce resources they had. On an extrastellar or galactic scale, this means that we don't really know what to expect from a civilization reaching these high Kardashev, around high Kardashev numbers. We don't know which of these paths it will take. We don't know if it will be able to cooperate internally, overcome problems, and expand outwards peacefully, or if it would go the path of war, civil or genocidal war, destroy itself or parts of itself, either partially or completely. And we have here kind of these 20th century's images of man-made apocalypse, of civil war in Guernica, and of course the atomic bomb unleashing powers of destruction. Both of these would reflect on possible modes of operation of these civilizations outwards. That is, we don't know if so-called aliens would be benevolent and driven by the will to assist us or whomever they find in peaceful and mutual benefit, or if they would actually be starved for resources, looking to expand violently, or at the very least, not even notice our existence as significant as a lower society and just destroy us and take over, kill us all and take over our resources, as exemplified by some of these other known images of non-benevolent alien expansion societies. We don't know which of these will happen. Again, the experience we have is only with humanity on Earth, and humanity itself has shown a variety of these possible behaviors. We should also say that even if some societies out there fear that other societies might be malicious or belligerent, it might actually be a more prudent course of action not to broadcast your existence and position to everyone in the galaxy. If you happen to live on a hospitable planet in a solar system which can give off energy and conditions for life, you might not want to advertise that to societies more advanced than your own, who might see that as an opportunity to come and take your land or take your planet while killing you off. So societies might actually exist there, but try to hide themselves from us. And of course, they might also be trying to hide themselves from us because they're coming here to kill us all and take our planet. All of these are perfectly legitimate and possible options, which are starting to grow more in the directions of social studies and strategic studies. But of course, the end result is what us physicists and astrophysicists can measure, which is so far not finding anything. Okay, another point is that it might not be the choice of an extragalactic society to invest itself in interstellar travel. Interstellar travel is a dangerous and expensive process. For one thing, it takes a very long time. We have, for an example here on the right, estimated travel times and time for travel. If you want to go fairly close in our interstellar neighborhood, as how long it would take you on your own crew, on your own ship, 1 year, 2 years, 60 years, etc. But then, of course, if you want to do it fast, you want to go in a very fast velocity, you want a reasonable acceleration, approaching the speed of light. As you go close to the speed of light, your time on the ship is progressing slower than it does for people outside. That's the Lorentz contraction of time effect, which means even if it takes you, say, 10 years to go only half a parsec away, and then 10 years to come back, during that time, people on Earth will experience about twice as long. And if you want to go further, if you want to go, say, maybe 100 parsecs away to a reasonable star which you found habitable, it will take you maybe a few tens of years to get there and back, but on Earth, it will be 1,000 years already for the round trip. So this colonization is not something that you can go to some star, colonize, come home and tell your family about it, your family and friends. Everyone will be dead by the time you're back. And it's a very, very sad process, which we might think societies will only be forced to do under very dire circumstances. Very dire circumstances. For example, if we are about to exhaust all the resources on our planet, or if the society on our planet is actively trying to get us off of it, as has also happened in human history, colonization by people expelled from any previous place where they could live. Communication is easier because you don't have to go anywhere. You just have to find the energy to broadcast there and back. But again, the ping pong of dialogue here will be years between successive messages. 4 years to our nearest neighbor, Proxima Centauri, 4 years there, 4 years back, even for a light signal. So a dialogue here will be very, very long, and one has to ask, would a society invest in this? And of course, we don't know. As I already said, we don't know whether a society willing to invest in this would do it for peaceful or for belligerent reasons. And so there are many questions here that we cannot yet answer, including, do we even want to be found by such a society? And are we ready to be found by such a society in the present condition of Earth and of the human race? These parameters are getting murky and kind of amorphous. They, again, have to do a lot with social issues. But in the end, they affect this parameter L from Drake's equation, which is saying how long can we expect to detect a new civilization capable of interstellar communication once it achieves that capability. And again, this can either be because it goes extinct or because it realizes that it wants to hide from us or from any number of other reasons. We just don't know what this parameter is. Putting all the numbers together, some of them, again, we have good understanding of. The star formation rate is a pure astrophysical observation number. So we know that that's about 10 a year. We have now more information about planetary existence and planetary conditions. So we can estimate this is at about 1. We have no idea really what FL and FI are, but we approximate them to be around 1. We expect FC to be of order 1 as well. So we see that basically from all these prefactors, we'd expect about 10 communicating societies or civilizations to form in the galaxy every year. That's a lot. Even if they only live for a very short time, we should still be able to see some of them. We do not yet see them, which brings the question of, again, why, where is everybody? Which of these parameters did we misestimate, maybe misoverestimate? And what does that mean for the remaining biological, evolutionary, and social processes and uncertainties required for these numbers to kind of match up with observations? So this field of astrobiology is in a great state of uncertainty, but not blind uncertainty. We kind of have ideas of what to look for. We're floating around ideas. We're suggesting mechanisms and we're measuring them wherever we can. And we're getting an idea of where to look for the answers that we don't yet have. So it's also an exciting time to be in the field. We can finally, 30 years ago, we had no planets. This was all just science fiction. Now, more and more of it is becoming science observation. So, 30 years ago, we only had the first number. Now we have 2 more. Biology is advancing. We're getting into more of these. So a lot of progress is being done in the field. I will finish by saying that some people don't like the Drake equation, and that's completely understandable. It's basically, like I said, replacing a number we don't know by a product of other numbers whom we do not know. So a variation has been proposed, the Seeger variation by Sarah Seeger, the astrophysicist here below, which is saying, let's not go into intelligence or communication or civil wars, and let's not meddle our physics with things that we physicists really don't understand. Let's ask what we can observe with a telescope or a radio telescope or any type of standard physicist apparatus. And most of these things we actually can observe, because even before humanity or life on Earth developed humanity, long before intelligence and radio communication and technology and all that, even just forming life on Earth transformed the planet considerably. Because the earliest bacteria was anaerobic. There was no oxygen free in the atmosphere. And the mere appearance of bacteria, anaerobic bacteria, released oxygen, then causing an evolutionary process by which aerobic life developed, and the ratios of carbon and oxygen in the atmosphere changed because of life on Earth. Life has this tendency of sucking and using up the resources it needs and giving off a lot of garbage in the sense of whatever organisms do not need that. So the chemical composition of a planet's atmosphere changes when life develops on it. And that we can detect. We can detect spectra, and we can analyze composition of atmospheric atoms and molecules. And so the Seeger equation is kind of a modification of the Drake equation. It says that the number of planets where we can identify signs of life, not necessarily communicating life, just signs of life, this n prime, will again be a product of a few numbers that we don't know, but they're maybe more within our reach. The number of observed stars is something that we can just count with a telescope, okay, a good telescope, but we can count it. The fraction of those which are quiet, that is stars which are not varying too much that they would destroy life, is something that we can measure. The fraction of those which have planets in the habitable zone is again something that we can start to measure, including the number of them that we can see, either because they're big enough or because they can be spectroscopically analyzed or astrometrically analyzed or discovered in any other way. Of these, there's a fraction of planets with life which we do not know, and the fraction of those whose life will modify the planets in ways that we can measure. So it's really these two parameters, FL and FS, or mostly this FS. FL was also in the Drake equation. This FS signals or signatures of gas replaces some of the more obvious unknowns in the Drake equation. We don't need to talk about evolution or intelligence or technology. We can just ask, will we notice that the atmosphere of the planet changed from a primordial composition to a composition indicating the presence of life? So this is a modification of the Drake equation and another one that's being used today in this field of astrobiology.
Ofik?
Yes.
Suppose we found a planet with traces of oxygen in its atmosphere. How do we know it is because life evolved there, or if it's because it had oxygen in its atmosphere?
So what you have to do here is not just measure how much oxygen there is, but measure kind of the composition of various substances in the atmosphere. And you can compare the oxygen levels or any level of a part of a molecule or atom to how much you would expect from just, say, a primordial composition, which is whatever is ambient in the star-forming region and then collapsing onto the planet. So there's you'd expect some ratio of, say, oxygen, nitrogen, and carbon just from what's produced in nuclear processes in the stars. You'd expect this ratio to be affected by how much of these different gases escape the atmosphere because of kinetic energy and temperature. You'd ask how much of these gases would you expect to be buried within the crust of the planet. Oxygen is a good example because oxygen is a very highly reactive atom. It reacts with many, many things. It's called oxygen because it generates oxides or acids and rust, basically. So typically, you don't expect to find free oxygen in the atmosphere. It would typically react with the rocky surface in the form of oxides. But you can compare that to the amount of carbon and other materials. You can compare the amount of CO2 to the amount of oxygen. And these types of comparisons relative to what you would have expected without life, you'll basically be ruling out alternative scenarios until you find that it looks like there's a process here that releases excess oxygen relative to what you would have expected. Okay, so for example, Venus and Mars have a lot more CO2 in the atmosphere relative to oxygen, relative to the Earth. Even though we all formed in a very similar stellar environment, the Earth locked up or consumed most of the carbon dioxide in the process of creating living material, carbohydrates and plants and photosynthesis and all those processes, releasing oxygen. So this photosynthesis is a crucial process. It takes CO2 from the atmosphere and puts oxygen into the atmosphere. And that only happens where you have these large-scale biological biomass performing photosynthesis and producing this effect. That's what you'd basically be looking for, traces of photosynthesis.
Okay.
Okay, I'll finish with this comic strip on topic, and trying to answer the Fermi paradox as well. And that's basically all we have for today. As I said, not very complicated mathematically. The tutorial will be slightly more mathematical because it will be discussing energy balances and the greenhouse effect. But that's in about, say, at 3:05, so almost 15 minutes. I'm still here for questions, but I'm turning off the recording. Oh, next week is, again, mathematically heavy. Next week, we start general relativity.